presented by Caltech.
So I can immediately use the fact that I know what the trig identity is for sums and differences of angles. So we get, so I could just split these up, cosine omega t, cosine KL1, and then it's minus sine A sine B, because there's a minus sign here, plus sine omega t, sine K, all 1. And then the same thing for the 1 through L2. And I'm looking at this for distances L that are large compared with A. This is referred to as the Fraunhofer region, the far field region here. So let me think of this in terms of the path length difference between L1 and L2, since that's what's going to make the interference. So I'm going to let delta L be defined as L2 minus L1, and I'll let L be the average of the two distances. Or we see that that means L1 is equal to L minus delta L over 2, and L2 is equal to L plus delta L over 2. And so then I'm going to rewrite these terms, and so I'm going to substitute these in for L1 and L2 in here. And so let me summarize what we get there. Cosine KL1, so just concentrate on this term, is going to give, is going to give a cosine KL times a cosine of K delta L over 2. Expressing that as L minus delta L over 2, cosine over here with the sign. Is everything okay?
Yeah.
Okay. And then plus the sine terms. Sine KL, sine K delta L over 2. So the cosine KL2 term will be the same as this, except there'll be a minus sign here because we have this minus sign changing to a plus sign. So our identities will get this. And likewise, the sine KL1 will be sine K L cosine K delta L over 2 minus cosine KL sine K delta L over 2. And the second one here, sine KL2, will just be the same thing except with a plus sign here, since this changes sign between L1 and L2. So I've summarized what these four terms are here. And there's a lot of things in common here, so let me look at what multiplies cosine omega t. So cosine omega t times, okay, so cosine omega t is going to have is going to have a cosine KL, cosine omega t here is going to have also, let's see, it's going to have a cosine KL, cosine K delta L over 2, and then this one, so there's going to be another cosine KL from this one with a sine K delta L over 2. So let's see, it's going to be, trying to do too many steps at once, clearly. Okay. So I get 2 cosine KL. Cosine KL, there's a cosine KL there, there's a cosine KL there. Oh, I see what I did wrong, okay. I got to consider these two terms, that's this with a plus or minus. Sorry. So it's a cosine KL that I've separated out here. There's a cosine K delta L that comes from both of these. And then the sine terms cancel because there's a minus sign here. So we just get a 2 cosine KL, cosine K delta L over 2. So that's everything that multiplies the cosine omega t. Okay, because these two guys are the same, so you get a factor of 2, and these two guys cancel. Now I consider the sine omega t term. And so we get a similar thing on that. So we get a sine KL down here, sine KL. So this part is going to cancel, and we're going to end up with a sine KL times sine KL times cosine K delta L over 2. Okay, so there's a common factor of cosine K delta L over 2. So we pull out the cosine K delta L over 2, and then and factor of 2, and then we'll have the cosine omega t, cosine KL, and a sine omega t, sine KL, and we can use our trig identity on that. And so we get goes 2a cosine omega t minus KL times cosine K delta L over 2. I'm just doing some trig identities here. And so the dependence on the path length difference is in this term. We see that the amplitude ranges from 0 to 2a in magnitude. Which we can go to minus 2a too. And it depends on delta L. Whatever delta L is, we'll get a range up to that. So if we ask for the intensity, of the light at our observation point P of theta, this is the square of the amplitude. Or at least proportional to the square of the amplitude in some way, depending on what kind of units we're trying to get out of this. And so this just follows from that the energy flux is proportional to the intensity is proportional to the electric field squared. And so this is deduced in the electromagnetic wave node. But I'm going to rely for here just on the fact that this is a common feature that we've been seeing, that the energy in a wave goes like the square of the amplitude, for example, of a string. When you have an oscillating string, the energy density would like the square of that amplitude. And likewise, when you think about it for waves on transmission lines. So this is a kind of a common theme that we have here. In quantum mechanics, it's the same thing. You have an amplitude. If you take the essence square of the amplitude, you get a probability density, which it could represent something like an energy density. Okay, so to get the intensity then, we just square the amplitude. 4a squared cosine squared omega t minus kl times cosine squared k delta L over 2. As usual, we'll average this over a cycle. Let's think. A little bit so you can see more. So as usual, we're more interested in sort of the average intensity, so we'll average over a cycle. You're supposed to. We'll denote that average with a bar over the I. And so that's just going to be 4a squared. This averaged over a cycle gives us a factor of a half. And then we have the cosine squared k delta L over 2. So I'm going to use the fact that delta L is approximately a sine theta. Theta is the angle to the observation point. And so this is approximately 2a squared cosine squared ka sine theta over 2. But I'm also going to consider just small theta. So if we just consider small theta, then sine theta is about theta, and so this is approximately 2a squared cosine squared ka over 2 theta. So for small theta, the argument of this cosine squared is just linear in theta. Of course, if you're going to do big theta, then the linearity goes away. And what the amplitude that looks like, the intensity looks like, let's say take 0 here and theta along this axis. So at theta equals 0, this has a maximum of 2a squared. So it'll go somehow like this, pull down. This is 2a squared. And it just oscillates like a cosine squared. Something like this. That's the same region. It's supposed to be the same feedback. If the source were not coherent and everything were just interfering in an incoherent way, then the intensity that you would get would be just A squared. There would be no theta dependence if there were no interference going on. And your average intensity would be A squared. So you can see that this is, when we get the interference, it's making the intensity have a structure as a function of theta that deviates from the average value. So the zeros, so this has zeros apiece. The zeros are at Ka over 2 times theta equals plus or minus 2n plus 1 over 2 pi for n equals 0, 1, 2. So that's just the zeros of this function here that I'm calculating. Or that corresponds to theta equals plus or minus 2n plus 1 over Ka, let's see, yeah, Ka times pi. So that's a little, maybe not the best way to describe it. Let's use the fact that K is 2 pi over lambda. And so then the zeros are at theta equals plus or minus 2n plus 1 over 2 times lambda over A. So that's kind of a nice physical looking way to look at it, but the zeros of our intensity follow a pattern that has even spacing for small theta, and it's at odd multiples of half lambda over A. So the figure in there here is lambda over A. That guides the scale of things. The maxima are likewise similarly at theta equals plus or minus n lambda over A. So the distance between two maxima here is just lambda over A, separated by lambda over A. So that's the double slit. We've assumed that we've got some coherent wave source represented by these plane waves here. In fact, you don't necessarily need to have a coherent wave coming in. You can also get these, what we call fringes here. So this is just as we observed in the demo in lecture. Remember we had, with a double slit, we had a pattern that, well, I'll mention this later. Okay, so I'll come back to it. I just want to make the point that an incoherent source can also produce fringes. If it approximates a point source. That is, if it looks something like this, we have some source that has some characteristic scale to it, W say, and it's some distance L away from our double slit. Distance A between the two slits. As long as W is very small compared to the other dimensions, we find that we'll get fringes, and the reason is just that even if the emission of the waves out of this are emitting waves that are incoherent with each other, that is, in arbitrary phase with each other, each wave produces the same intensity pattern. So consider, say, a single photon, if you like, gets emitted, it produces a fringe pattern on the screen. Then another one comes along at an arbitrary time later, it produces actually the same fringe pattern. And same interference pattern. And that's because it's a point source. If it were extended, it'd all get destroyed. I mean, here we have a monochromatic wavefront, a coherent wavefront that's all in phase with each other at every point on the wavefront. So all the phases reaching the slits are the same. And so even though this is a plane wave, which is infinitely extended, you get the fringes. You get the same sort of thing out of a point source, even if it's not coherent. Because once the waves reach here, it's like each wave is a coherent thing across the two apertures, and you get a fringe pattern from that wave, and then you get the identical fringe pattern from the next one that comes along. And the criteria, the condition, is worked out in the book, so I won't work it out here, but it's just that this characteristic size of your source must be much less than 2 times L lambda over A. And that's just from the geometry. So you can work that out just from the geometry. You want to have it such that something from this point on the source and something from this point on the source are close enough so that they don't make any difference in the path length to the screen. Okay, so I was about to point out what we saw in the demo. What we saw in the demo was we saw a bright spot, another bright spot, another bright spot, but we saw this was broken up into little spots. When we did the double slit experiment. And the point is that what we see is 2 effects. A real double slit has 2 effects. One is the finite width of each slit. That is, each of the 2 double slits is like a single slit. And the double slits. So we have the diffraction from a single slit adding to the diffraction off of a double slit. And so and then we get a pattern. We get from this. So we get 2 single slits of width W. The 2 slits are separated by A, and we get diffraction from both situations, and it looks like a central peak, another peak, and so forth. So these are from the single slits. So this is the intensity pattern you observe as a function of theta from a single slit. From the double slit, that gives substructure that it looks like this. And remember in the demo, what we saw was the little dots and immersed in the bigger dots. So the big structure is just due to a single slit, and the little structure, the fine structure, is due to the fact that we have two slits that are varying with each other. So we can be a little more general than this now, since we know it's all geometry. It's all calculating differences in path lengths, that is calculating different phases. So we can be more general. So let's try a different kind of aperture. So we're going to consider the limit in which the distance to the observation, so L is a characteristic distance to the observation, and A is the aperture size, a characteristic description of the aperture size. Aperture size. Assuming a coherent light source coming onto the aperture, okay? Or like a point source that's effectively coherent. This regime is referred to, as I mentioned, as the regime of Fraunhofer diffraction. And we'll have a little demo on sort of another case on Tuesday. But let's concentrate on Fraunhofer diffraction. And let's consider a circular aperture. The book has a little discussion of this, but doesn't really calculate it for you. And it's actually rather important because we have microscopes and telescopes that all have circular objectives. Okay. So let's see. So we assume that we have an incident plane wave. With a wave vector k sub I that has some magnitude k, and let's assume that it's going in the z direction. And we're going to let this hit a circular aperture in the xy plane. So the idea is we have a circular aperture here in the xy plane. So x, y plane, and the incident beam is coming in here along the z direction. So the z direction is pointing up like that, x. And so this is the incident plane wave coming up along z. And we're going to, for simplicity, of course, we're going to center our aperture at the origin. It would be silly to do anything else here. I don't want to make life too complicated. And I want to ask for the intensity, say, of the light at point P described by vector x. Okay, so P is the point x equals x, y, z. That's our observation point, which is far from the aperture. Because we want to do this Fraunhofer diffraction. Basically, we want to make our lives easy in the calculation. It's often a perfectly reasonable assumption for what the things we typically do. And let's let x prime be a point in the, so x prime we're going to take to be some point in the aperture. See, the issue is that we're going to have to take our coherent wave that's coming in, hitting the aperture, everything out here is blocked. So it's just a hole. So it's going to come in and we're going to get light over here at point X, but that light that we get over at point X is going to be a superposition of the light from every point on the aperture. Think in terms of Huygens principle, if you like. And every point on the aperture is going to have some phase of the light when it reaches point X. And so we're going to have to add up over all the phases on the circular aperture. So let's let X be a point on the aperture. X, Y, and of course Z is equal to 0. X prime, Y prime is equal to 0 since it's in the XY plane. Point in the aperture. Okay, so at observation point P, we're going to have, since it is far enough away, we're going to have an approximately spherical wave. If you go far enough away, this aperture is just like a point, so you just see the spherical wave coming out from the point. With wave vector k along the observation direction. To capture the interference, we need to integrate the phase factor e to the I k dot x minus x prime over the aperture, over all the sources on the aperture, or Huygens sources. So we need to integrate this phase factor to see what the sum is going to be. The sum over all the phase differences from sources on this aperture. So let's see, so this factor that we have in this phase factor, k dot x minus x prime, as long as r is much bigger than a, we can write this first product, k dot x. K is approximately along the x direction, it's our observation direction here. So that first term is approximately kr. And then the other term is k dot x prime. Okay. We're looking at the k vector that's going from the aperture up to the observation point. It's following that direction. Okay, but not, so what we want to do now is examine this term, because this is going to end up being something we have to integrate over the aperture. Let's call that k, magnitude of k, times the direction of the observation point, which is just x. So put an x hat on it, okay? Okay. I don't know how to do this notation. So this isn't the basis vector in the x direction. This is a unit vector. It isn't the basis vector in this direction. It's a unit vector in this direction. Be clear, yeah.
What is the
Little r. Little r is this distance. Sorry, forgot to put that on there. And so we can write this as k times rho times cosine of gamma, where rho is just the magnitude of the x vector. And we also have that the size of the aperture is A, if the radius of the aperture is A. And cosine gamma, so gamma is the angle between x and x prime. So let's see, so we have to figure that out. So let me make another drawing here. Z, x, y, x. And so let's see, we draw these guys. So x is some point up here. And x prime is some point here in the plane. So gamma is the angle between the two. That's what we're taking the cosine of. And so x has polar coordinates, call it theta, and maybe phi. X prime has polar coordinates. Well, theta prime is pi over 2, since it's in the xy plane, and phi prime is whatever this angle is. And so cosine gamma we can write as cosine theta prime plus sine theta sine phi theta prime cosine of phi minus phi prime. So that's the general formula for the cosine of the angle between two vectors, given their polar angles. So if you've never demonstrated this, it'd be a good idea to demonstrate it. You can just kind of write the Cartesian coordinates of each in terms of polar coordinates, and this is just a dot product between the two vectors, the two unit vectors in the two directions. Okay. So you consider a unit vector in this direction, a unit vector in this direction, express their xyz components in terms of theta and phi, take the dot product, and you get this. Okay, so theta prime is equal to pi over 2. So this first term goes away. As cosine pi over 2 is 0, and so you get sine theta times 1 times cosine phi minus phi prime. But we have circular symmetry here, so let's make our lives easy. We can choose, since we have circular symmetry, we can choose our origin in phi to be any direction we want. So let's choose our origin in phi to be such that phi is equal to 0. just to simplify our lives. So we're just taking our observation point to be along phi equals 0, and we know that the amplitude there is not going to depend on phi. It's going to depend on choice of phi. And so we're left with cosine gamma equals sine theta cosine phi cross. Okay, so the magnitude of the wave at x then x will be proportional to the magnitude of the electric field, since we're talking about electromagnetic waves. And so we use the electric field as our amplitude. And so that's going to be proportional to something. I'm not going to try to work out I'm not going to worry about what the proportionality constant might be. So it's approximately a spherical wave in the r direction, expanding out with r. And then we have to add up all these phases. So we integrate over the disk, over the aperture. 0 to 2 pi, d phi prime, e to the minus I k rho, sine theta, cosine phi prime. So that's going to be what our amplitude is going to look like at our observation point. And all we're doing is the same kind of geometry we've been doing before. Just looking at phase differences. Yeah.
Sorry, that formula usually applicate times x minus x prime. Where did that come from?
Where did this come from? So this is just from the wave, e to the I k x minus omega t. So it's precisely this phase that I pulled out of here. Omega t is common, so I'm ignoring that. Okay. And so I just have an e to the I k dot x. But the x minus x prime comes because I am considering this source, the effect of a source here. So this vector is x minus x prime. So this tells me that's what gets multiplied times the if the source is over here, it's e to the I k x minus x prime rather than just e to the minus k here. Okay, so we stare at this integral, we stare at this integral, we stare at this integral. Oh, well, okay, you could probably do it with a series solution. We know what the series expansion for E is. If you do that, and if you look at the Bessel function note, you will discover that you get a Bessel function. You will get the series expansion for the Bessel function. That maybe isn't too surprising since we have a problem with circular symmetry, and that's where Bessel functions showed up before. So the zeroth Bessel function, evaluated at some argument u, can be written as the integral from 0 to 2 pi d phi e to the I u cosine phi. And you can see that's precisely what we have here as well. There's some u is this k rho sine theta with a minus sign. And so therefore, E is, proportional to e to the I k r over r times integral from 0 to a, so I still have another integral to do, rho d rho, of j0 of k rho sine theta. That's effectively what u is. Okay, there's a sign difference between here and here, but you would discover that the sign goes away. J0 minus x is equal to J0 of x. J0 is an even function in its argument. You would discover in doing this series expansion that it's only the even powers that contribute. So everything would hang together. Okay, but we still have an integral to do, an integral of a Bessel function. So again, you can play with things and do series expansions and look at what you get. And you would discover the following relation if you worked hard enough. 0 to a rho, J0 of rho, d rho. So the integral of the Bessel function with this factor of rho out front gives another Bessel function, J1, evaluated at the upper limit here. Or integral from 0 to a of rho J0 of k rho sine theta d rho. So I'll just let x equal k rho sine theta here and do a substitution of variable. And I get 1 over k squared sine squared theta from these two parts here when I do the substitution. And integral from 0 to ka sine theta of x, j naught of x dx when I do that substitution. And then I look up here and see what that gives me. So that'll give this times this, okay, times j1. So I'll give an a over k sine theta times j1 of ka sine theta. This is just that a there. Okay. And so that's the answer then. Is proportional to e to the r over r a squared j1 of ka sine theta divided by ka sine theta. And just a remark that if we looked at our series expansion for J1, we would find that the limit as z goes to 0 of J1 of z over z, which is what I have, the way I've expressed this here, is just equal to 1/2. So the limit of theta going to 0, that is a factor of a half. For small theta, we can again approximate sine theta as theta. For small theta, J1 of Ka sine theta is approximately J1 of Ka theta, so the argument then is just linear in theta. And then we can notice that, so J1 has zeros. For particular values of theta, that will go to 0, just like we had for the double slits. So for small, there will be rings of intensity. So we'll get a diffraction pattern like we saw in the demonstration on Tuesday. We'll have rings of brightness. So bright here, bright here, bright here. Just like what we saw when we looked at, say, the Michelson interferometer. Let's see. So the rings of intensity. And so there will be places where the intensity goes to 0, and there'll be rings where it's bright. The first ring where it goes to 0 is going to be at the first 0 of the Bessel function. Of our Bessel function. And that first 0 will correspond to Ka, I'll call it theta sub 1, and the first 0 is at 3.832. It's some number, that's where the first 0 of the first Bessel function happens. So let me figure out what theta 1 is here. Okay, so with K equals 2 pi over lambda, put it in some more intuitive units, and capital D is equal to 2a is the diameter of the aperture. We find that theta 1 is equal to 3.832 divided by 2 pi times lambda 2 over d. So the 2 cancel, so you get 3.832 over pi, which is close to 1. It's actually 1.22 lambda over d. This central spot is known as the Airy disk. And it's of some importance in things like telescopes because it tells you when you can resolve, say, 2 stars that might be close together, 2 objects. So there's something called the Rayleigh criterion. It states that 2 objects are barely resolved, just barely resolved, if the Airy spot for 1 is central disk is centered on the first dark ring of the other. That is, if there's angular separation in the sky, delta theta, which is a telescope, and we're talking about stars, is 1.22 lambda over d, because in this case, then we have the Airy disk of 1 looking like that, and if that's centered on the first dark ring of the other, it's supposed to be a ring. That's the Rayleigh criterion for the resolution of of a telescope. Or any optical